Hi everybody, welcome to week 11. Let's just jump in. Okay, so a little bit of housekeeping. This week, not today, we'll look at the E and the Pi project, and then next week we'll look at the shooting a basketball project, so we'll be back on track. I want to show you a sneaky trick though that's going to be useful for the E and the Pi project. Okay, so take a look at this double integral. Notice my integrand has got two functions that are multiplied. One of them only has x's and the other one only has y's. When this happens, you can do this sneaky trick. And here's the idea behind the sneaky trick. Notice in this integral, the first thing I need to integrate is with respect to y. That means that this function that doesn't have any y's in it is a constant, and I can move it outside the integral. Now I can't move it all the way out. I can only move it outside the first integral. I can't move it outside the second integral because that is with respect to x. And so x is a constant with respect to that. But with respect to y, that sign of x is a constant. So I'm going to move it out. So there. And this is from 0 to pi. Okay. So now the way this stands, I want to do this integral, cosine of y dy, and then after I'm done doing that, I'll take that result and multiply it by the sine of x, and I'll do the integral. But notice now, this integral, after I evaluate it and put the 0 and the pi in, it's going to be a constant. It's a constant. So I can move it outside of that integral. So I'm going to do that. So 0 to pi cosine of y dy times the integral from 0 to pi over 2 sine of x dx. And now these are multiplied together. Very sneaky. You can't do this all the time. Only in this special case where if one function only has one variable and the other function only has another variable and they're multiplied. If these were added, no go. You would still have to do the integral. But the multiplying makes it act like a constant times the functions, and that you can pull out of an integral. So I'm going to invite you guys to finish that out and work it and see how it goes for you. Okay? All right, moving on. There's the connection between E and pi that we'll look at in class this week. And here's the new material. So now we're going to look at what are called vector-valued functions, which means that their output is a vector. And so the output here is written as a vector, and of course you can write it with the IJK notation. Like that if you want to. I put in a single value, which we think of as time usually, and I get a point in space, a vector, a location in space. So these things describe motion. So think about a little fly flying around in the room, or the space shuttle or something like that. This gives me the motion of that fly flying through the room. Let's look at a few examples. You did look at these in Calc 1 in Math 262, but you only looked at them with two variables. And I hope you remember that this function is a circle, gives you a circle. In fact, it's the unit circle. When t equals 0, this gives you the point 0, 1, and as t increases, this point moves around in a circle, counterclockwise in standard position. Okay. When I add a z component, though, now I have something that moves in 3 space. The x and the y still move in a circle, but the t value gets larger and larger and larger. So if I think about this in 3-dimensional space, it starts off and it starts to make this circle, but it gets higher and higher as I go, like that. So this is a spiral. Or let's not call it a spiral, let's call it a spring. says it looks like a spring. Okay. When your x, y, and I could add a z component here, when they're linear, this is a straight line. Okay. And then when I multiply something inside the argument, that changes the velocity. And when I multiply something outside, that changes the width. And when I add a number, that changes the position. So let's take a look. Let's go into GeoGebra and see if we can graph a few of these. Let's see, GeoGebra 3D. Let's make this a little bit bigger so that we can see it better. And now I'm going to graph a curve. So let me just graph the sine of t, cosine of t, and t. So there's my spiral. Okay, and you can see on this first line up here, the t started at 0 and it moved up to pi. So this goes around the circle one time. You can see from the top it looks like your circle, but the t makes this thing rise as it goes. So let's change this. Let's make this a 3t. I'm going to close that down and make a new curve. And now you can see it goes around 1, 2, 3 times. So it's gone 3 times as fast in the same amount of time, because I'm still going from 0 up to pi when you look at the t values here. Okay, so my spiral goes 3 times as fast. Let's make a third one. Let's do, in fact, let me leave this on and let's put a third one on. Let's make it 4 times sine of 3t and just cosine of 3t and t. So you can see it's wider in the x direction. The red is the x. It's wider in the x direction and stayed the same width in the y direction. That's the number I have on the outside there. And then let's do one more. Let's do sine 3t plus 1 and cosine of 3t plus 4 and t. And you can see it's moved over. It's exactly the same thing, same shape, you can see, but it's moved over 1 unit in the x direction. The center's 1 unit in the x direction and 4 units in the y direction. So there's my 1 for my x and my 4 for my y. So you can see how this changes these around a little bit. Okay. All right, back to this. Okay. All right. In general, you can kind of see how these things work. All right. If this is a graph of x of t, comma y of t, okay, then negative x of t is going to flip it horizontally, and negative y of t is going to flip it vertically. So if I look at this, this flips horizontally and then flips vertically, so I should be looking for something that comes around like that. My horizontal flip will make this part move that way, and the vertical flip will then turn it upside down, which will make it go that way. So that's why that's the answer to that one is C. On the other hand, for number 2, only the x is multiplied by a negative. So this little part that goes like this now is going to go like that. So let's find that. We already found this one. So it looks like right here, same center. Okay, I'll just do one more. X of t plus 1 y of t is going to move that 1 unit to the right. So if I've got the exact same graph going around counterclockwise, it should be moving 1 unit to the right, but not up. So that looks like that would be right here, okay? So that's how these things work, by changing these. But really, I think if you do a lot of these in GeoGebra, you can see a lot more easily than thinking it through this way. But you should get to the place where you can start to visualize these. Now let's go on. Let's compare these to motion. Okay. So here's a homework question. We've got two particles traveling through space. Okay. Here's the graph for the first one. Here's the graph for the second one. And I want to know two things. Do the lines intersect and do the particles collide? I'm going to answer the collide question first. In order to collide, they need to be in the same position at the same time. So if I set my x values equal, if they're in the same position, their x values are equal. So if I set my x values equal, and my y values equal, and my z values equal, whoops, that's an 8t. I can solve these for t. When I solve the first one for t, that's going to give me 4 equals t. And when I solve the second one for t, I better get 4 for t. If they're going to collide, I should get the same t value for all three of these. So let's see, 6 plus 2 is 8, and 2t plus t is 3t. That gives me 8/3 equals t. So no, they do not collide. That's a good thing, because we don't want collisions. We want to prevent them if we can. Okay, so they do not collide. They might be at the same place, but they won't be at the same place at the same time, because we got different times for the x and for the y. Now, if I want to know if they intersect, I need my x's to be equal, but the times might be different. Okay, so I'm going to set -1 plus t equal to -5, and I'm going to change that to an s, -5 plus 2s. And I'm going to do the same for the y's. 6 minus t equals -2 plus 2s. And I'm going to do the same for the z's. -14 plus 8t equals -1 plus s. And now I have what's called an overdetermined system. It's two variables, but I have three equations. So I need to find out if I get the same s and t for both of these. So I'll clean this up a little bit. The first equation is going to give me t minus 2s equals -5 plus 1 is -4. That's an arrow. The second equation is going to give me -t minus 2s equals -2 minus 6 is -8. And the third equation is going to give me 8t minus s equals -1 plus 14 is 13. And I need to solve this system and see what I get for my t and my s. So let's see. I'm going to add the first two equations together, and that'll give me -4s equals -12, and so s equals 3. And then from the first equation, that's going to give me t minus 6 equals -4, so t equals 2. And then I'll check to make sure that that works for all three equations. Okay, so t is 2, s is 3. So in the first equation, 2 minus 2 times 3 is 2 minus 6 is negative 4. In the second equation, negative 2 minus 2 times 3 is negative 2 minus 6 is negative 8. That works. And I need to check the third one to make sure. So 8 times 2 is 16, minus 3 is 13, check. So when time equals 2, the first particle will be at a certain point, and then when time equals 3, the second particle will come through and hit that same point. So yes, the paths intersect, but not at the same time, no collision. Ready? Okay, moving on. Okay, what does this have to do with calculus? Well, if our vector valued function is a position, then the derivative will give me the velocity, and the derivative will be a vector. I'll show you how to do this in a second. The second derivative gives us acceleration, just like in Calc 1. And that will be a vector. The length of the velocity, not the length of the acceleration, the magnitude of the velocity is speed. You learned in Calc 1 that the absolute value of velocity was speed. Okay, this is the extension of that. The magnitude of the velocity vector is speed. And the distance traveled is going to be from your first time to your second time, the integral of the speed, dt. So notice this is speed, not velocity. If I just integrated, let me make that a 1. Doesn't have to, could be anything. If I just integrated velocity, this gives me displacement. Not distance. So for example, if I were just in 2 variables and I had cosine t, sine t, whoops, sorry about that. And I integrated from 0 to 2 pi. If I integrated from 0 to 2 pi, that function, the derivative of that function, that would give me 0 because I wouldn't have moved. No displacement. On the other hand, if I integrate the length of that, I would get 2 pi because I would travel around the circle 2 pi. And actually up here I wouldn't get the number 0, I would actually get the vector 0. I wouldn't even get a number. Okay, because r prime is a vector. Let's talk about how to calculate these. I don't think I put a slide in for that, but taking the derivative is very easy. So let's do an example where we take the derivative. Suppose that my position vector is, let's do it, cosine t, sine t, t. So I've got a spiral. All right. R prime is very easy to calculate. I just take the derivative of each piece. So the derivative of cosine is negative sine. The derivative of sine is cosine. The derivative of t is 1. So there's my r prime. Okay. So this is the velocity. Notice the velocity is a vector, because now not only the speed that you're traveling counts, but the direction you're traveling counts. If you're going north, trying to go to Flagstaff on I-17, and you're going south, you're not going to get to Flagstaff very soon. All right, my acceleration, easy again. I just take the derivative of each component of the velocity vector. So the derivative of negative sine is negative cosine. The derivative of cosine is negative sine. The derivative of 1 is 0. There's my acceleration. All right. My speed, if I take the length of my r prime, I do it the same way we did when we first learned about vectors. I'll take my x component and I'll square it. I'll add my y component and I'll square it. And I'll take my z component and I'll square it. And then I square the whole thing. So I hope you see that this will give me a positive sine squared t plus a positive cosine squared t, which will become a 1. So my speed is a constant square root of 2 in this case, even though my velocity is not constant, because at any given time I have different values for my x and my y there. But my speed is constant, even though my velocity is not. If I want to go from time equals 0 to time equals 2 pi and find my distance traveled, oh, let me just say also this is speed. My distance traveled, I'm going to take the integral of my speed dt, and that'll be square root 2 times t from 0 to 2 pi, which will be square root 2 times 2 pi minus square root 2 times 0. So 2 square root 2 pi is distance traveled from time equals 0 to time equals 2 pi. So that's all you have to do, just the same way you would probably expect to do it if you had seen these and not had me tell you anything. All right, let's see. Suppose, oh yes, we've got a vector that measures horizontal distance. Y measures my distance above the ground. So this is just a 2-variable function. Okay, at time equals 0 in seconds, a projectile starts from a point h meters above the origin with speed z meters per second at angle theta to the horizontal, and we have a path. Here's the x value of the path. Here's the y value of the path. Maybe like a basketball, huh? Let's take a look at that later on and see. All right, so I could write this as a vector. I could write it as v cosine theta t in the x direction, h plus v sine theta t minus 1/2 gravity t squared in the y direction. Okay, if I know that this comes out to be these formulas, can we answer these questions? Where does it hit the ground? Let's answer when it hits the ground first. It hits the ground when y equals 0, right? So I would solve my y equation for 0 to find out when it hits the ground. After I find that, then I would plug in here to find my position. So Calc 1 questions. Its height when it was shot. That's my y value when time equals 0. G, V, and H we can find from looking at the equation. We can see that H is equal to 6. To find V, there's my V, sine t equals 34. Oops, not t, V sine theta. I should have known that. And I can also see that V cosine t equals 29. So I can solve that system of equations. Actually, I can solve it quite easily. If I square both and add together, I get V squared sine squared t plus V squared cosine squared t equals 34 squared plus 29 squared. So v squared is going to be 34 squared plus 29 squared. So I can find v from that. And if I divide these two, v sine theta over v cosine theta, that'll be 34 over 29, but the v's cancel, and that gives me tan theta. So I can take the arctangent of 34 over 29 to find out my v and my theta from there. How about maximum height? Whoops. Let's come back to this. Maximum height, that's when y prime equals 0. So I'd find y prime and set it equal to 0. How far has it traveled horizontally at its maximum height? Oh, first I would find t, then plug in for y. How far has it traveled horizontally at its maximum height? I would set y prime equals 0, find t, and then I would plug into x to find how far it's traveled horizontally at its maximum height. So I'm not going to go through the math for that. The math for this is pretty simple math, but I wanted to show you the process, especially this, because this is something you're going to see in differential equations quite a bit when you get into simple harmonic motion. And so you'll be doing a lot like that when you get to there. Okay. All right, moving on. The geometry of motion. This is going to be big for physics for you. R prime is tangent to the motion in the forward direction. R double prime has two components. It has one component that's in the direction of forward motion. It has one that's that points in the concave side of motion. And these guys are going to be perpendicular to each other. Okay, so why has R prime got two pieces like that? Well, think about this. Force is mass times acceleration, right? It works even if these are vectors. So if I have a thing that's traveling, I'm going to have a component that's going to move it forward. That's my tangential part. And then I'm going to have another part that's going to keep it off of that straight path and force it to curve. And that's my acceleration part. So just wanted to point that out. You can break R prime into two components. How would you do that? Oh, you would look at projections. Notice that R prime is tangent to the motion in the forward direction. So you would take R double prime onto R prime. So you're finding R double prime parallel. And then to find the part that's on the concave side, you would take R double prime perp. Remember that from the very first couple weeks of class? It was on the first exam. Yeah, I don't think you have any homework like that, but that's important. That's an important fact to know. All right, moving on. We're going to do Emily in class as an example, so I'm going to skip that, and let's go on to the next part. So that's motion. Now we're going to talk about vector fields, and the rest of our semester is going to be spent working with vector fields. These can represent forces, velocities, charges, all kinds of things. And what they are is a vector whose input has two or three variables. So its input is a point, either in two variables or three variables, and its output is a vector. Okay. These could be gradients of a function, and they're used to measure how things flow, how things move. Okay. We'll look at an example on the next slide. Yeah. So here's a picture of a vector field. Okay, at these different points, I have different vectors. Okay. Let's see if we can figure out which vector field this is. I'm just going to draw examples of these. Okay? So this vector field is x times I. So at any given point, so if I'm at the point 1, 1, for example, that vector would be the vector 1, 0. So that's 1 unit long, and it doesn't have a y component. If I'm at the point 2, 0, the output would be 2i. If I'm at the point, 2, 1. If I'm at the point 3, 1, that vector would be 3i. That doesn't look like this, does it? Let's do a few more examples, though. If I'm at the vector -1, 0, now I am at 0. That's going to be -1i. So there's my vector. Let me get rid of that little piece. Whoops. If I'm at the vector -2, 0, that's twice as long. Okay? And so forth. So it's not that one. Let's look at this one. xi minus yj. Suppose I'm at the point 1, 1. Then the vector is 1, comma, -1. So it'll go 1 unit to the right and 1 unit down. If I'm at the vector 2, 1, then it will give me 2, -1. So it'll go 2 over and 1 down. If I'm at the point 1, 2, it will go 1 to the right and 2 down. 1 to the right and 2 down, so it'll point there. Doesn't look like this, so it's not that one. Okay. How about the vector field -x plus yj? If I'm at the point 1, 1, it will give me a -1 plus 1. Points that way. Actually, it goes right to the axis. If I'm at the point 2, 1, it will go -2 plus 1, so it will point to the same thing. If I'm at the point 2, 2, it will go -2 plus 2. That doesn't look right. Let's try this one. If I'm at the point 1, 1, then I'm going to go -1, -1. If I'm at the point 2, 1, I'm going to go -2, -1. If I'm at the point 2, 2, I'm going to go -2, -2. That doesn't look right. Must be this last one. Can't be that one. Because if I'm at the point 1, 1, then I'm going to go 1, 1. That's going the wrong way. I think I made a mistake on this. I think it's this one. Let's come back to it. I'm so sorry. If I'm at the point 1, 1, I go into the origin. Okay. If I'm at the point, yeah, that's the only one that goes in the correct direction. Let's check something over here. If I'm in the second quadrant, that means my x value is already negative, so making it a negative makes it a positive, so it'll point in. And the y is positive, so it'll point down, so it'll point towards the origin. Those look right. If I'm in the third quadrant, my x value is positive, so the negative will make it a negative, so it'll go to the left. My y is already a negative, so making that negative a negative will make it a positive, so it'll point in. And if I'm in the third quadrant over here, my x is negative, so making that negative a negative will make it a positive, so it'll go in the positive direction. My y is negative, so it's pointing down, So making that negative a negative will make it point up, so it'll point in. It's this one. I'm so sorry about that. Okay, whoops. Another thing that we're going to look at are the flow. So if I have a vector field, let's just draw this vector field, yi plus xj. So let's just put a few vectors here. If I'm at the point 1, 1, then the output of that will be the vector 1, 1, so it'll go that way. If I'm at the vector 0, 1, then that will be the vector 1, 0. If I'm at the vector 2, 1, that will give me the vector 1, 2, so 1 to the right and 2 up. And you can kind of follow these arrows. You can see that I'm getting something that looks kind of like that. If I'm at the vector 1, negative 1, the output of that will be negative 1, comma 1. So negative 1, comma 1 goes that way. If I'm at the vector 2, comma negative 1, that'll give me the vector negative 1, comma 2, which goes that way. You can start to see that these vectors flow around like that. Okay, and as you fill in more of these vectors, you will get pictures as you follow the arrows. The arrows will kind of give you a flow, and you'll see that you'll get a flow that looks like this, a flow that looks like that, and so forth. Okay, we'll look at more of those in class though. That's all I've got for the video. I'm trying to make these a little bit shorter, and then we'll do more examples in class on Tuesday and on Thursday. And again, we're doing the same thing on Tuesday and on Thursday, but you are welcome to join both classes if you want to. So I'll see you in class. Thank you so much. Bye-bye.